Hello and good evening, everyone. I'm John Holler, the president of the museum, and on behalf of the trustees and our members and our staff, it's a pleasure for me to welcome you to the museum tonight. How many of you are here for the first time? Quite a few. Well, we want to say a special word of welcome to all of you who are coming for the first time this evening. And for those of you who are not coming for the first time this evening, we have that preview film of Revolution in part to explain the construction and the disruption downstairs. If you're accustomed to coming in the front door and all of a sudden tonight you were greeted by a giant red sign that said, "Danger, do not enter," it's not because we don't want you here. We're very glad that you're here, but it just happens that we are thick in construction of with Revolution, and that will open toward the end of the year. And it's a very, very exciting development for us here at the museum, and we're delighted to bring you at least a sneak preview of it tonight. There are several people that I'd like to thank briefly as we get this program underway. First of all, I want to thank a range of people who are responsible for the creation of the Affiliated Historian program here at CHM. Dr. Michael Riordan, who's the adjunct professor of physics at UC Santa Cruz and a lecturer in the history of the philosophy of science at Stanford University, is an active member of the Semiconductor Special Interest Group here at the museum and was instrumental in envisioning and setting in motion this program several months ago. And I want to thank Dr. Riordan in particular for helping us to envision and to execute on this program. The entire SemiSig has been incredibly supportive, and I want to thank all of them. Many of the members are here tonight. And I especially want to thank their staff director, Rosemary Rameli, who has been absolutely tireless in putting this program together this week. I also want to acknowledge our senior curator, Dag Spicer, who was also very active in setting this program up. Second, I want to say thank you, a major thank you, to the IEEE Santa Clara Valley section, and to Dick Aarons, a member of the executive committee, for their generosity in funding this event and also their strong belief in a growing partnership between the Computer History Museum and all of the aspects of the IEEE. We're working together in about a dozen ways now, with more to come. And if you're an IEEE member, I think you've got a lot to look forward to in the future with the partnership between the museum and the important work that you do as IEEE members. The section was joined by the IEEE Foundation as a joint sponsor of this event, and they are joined in partnership tonight by three other IEEE societies. The Electron Devices Society, who is chaired locally by Manoj Ratho, the Computer Society, who is chaired locally by John Swan, and the Solid State Circuit Society, who is chaired locally by Kiran Gunams. All of them are here tonight. John and Kiran, I saw you earlier. Thank you very much. And also Dr. John Vardalos, who is the research historian for the IEEE History Center and is here in California. John, thank you, and the IEEE History Center for your support. I also want to thank our distinguished panelists, Les Videz, Lou Turman, and David Hodges, for their participation in their work. They've put in a lot of work to prepare for tonight. Ross Bassett will be giving them a more formal introduction in just a moment. I just wanted to say a personal word of thank you now on behalf of the museum, so thank you. Tonight kicks off 2 nights of programming featuring our first affiliated historian, Dr. Ross Bassett of North Carolina State University. Tonight, of course, looks at the foundation of the digital age, truly the foundation of the age, and the development of the metal-oxide-semiconductor transistor. And on Thursday night, we'll examine the close relationship between the great universities MIT and the IIT, their Indian graduates, and their joint role in shaping computing history. And I hope you'll be back on Thursday night and join us for that program as well. And now let me make the official introduction to tonight's program. Resident scholars are an important part of any great research institution. This museum supports an enormous amount of research every year into many aspects of computing technology, computer history, and especially the sweeping social impact that computing has had on humankind. Until now, however, we have mostly hosted and supported the research of others. We have not enjoyed the capacity to host our own technology historian in residence, although it has long been and remains an ambition of ours. Happily, with the support of the IEEE and the willing participation of Dr. Ross Bassett, we are launching our affiliated historian program tonight. It takes a lot of guts to be the first at anything, and Ross Bassett certainly has the bumps and bruises to show for being the first affiliated historian. But he has shown the willingness to undertake that, and he has done it with great collegiality and good humor, and Ross, we appreciate that very much. Dr. Ross Bassett is the director of the Benjamin Franklin Scholars Program at North Carolina State University. He received an undergraduate degree in electrical engineering from the University of Pennsylvania, his master's degree in history at Cornell, and a PhD in history from Princeton. His work in the technology field includes 8 years as an engineer in IBM's semiconductor facility in East Fishkill, New York, before he began his graduate study. He writes extensively and speaks frequently on a variety of topics related to the intersection of history and technology. His work in this field has been supported by the IEEE's Life Member History Fellowship. Tonight, the centerpiece of his scholarship will be on display. It is represented in his book, To the Digital Age: Research Labs, Startup Companies, and the Rise of MOS Technology. It tells the story of why this particular technology became one of the most dominant technological features of our time. Currently, Dr. Bassett is working on a history of Indian graduates of MIT, as I mentioned, how they helped create the Indian Institutes of Technology, modern technological pursuits in India, and the important role that they play in the American technological industry. That will be the subject of the program on Thursday night. Tonight, it's all about MOS. Dr. Bassett is going to introduce it to us now. Please join me in welcoming our first affiliated historian, Dr. Ross Bassett.
Thank you all for coming tonight. Thank you, John, for that generous introduction. So we're here tonight to talk about the history of the MOS transistor, the metal-oxide-semiconductor transistor. It probably is a device that needs no introduction to most of you. It is the fundamental element of digital electronics today, and in many ways you could say it's the foundation, the base technology of American society. And the MOS transistor is also, I would say, an interesting story. It's a story of the ugly duckling that turned into a swan. Or another way to say this, if Hans Christian Andersen had been both a teller of story tales and a business professor, he would say, the MOS transistor is the story of an ugly duckling that turned into a several $100 billion a year industry. 50 years ago, last month exactly, the MOS transistor was first introduced at a public semiconductor conference by the engineers at Bell Labs, Dawan Kong and John Atala. Now, I want you to engage in a little thought experiment with me that I want you to imagine all of us going back from the year 2010 to that conference in 1960 at Carnegie Institute of Technology, as it was called then, in Pittsburgh. And we're going to tell everyone there two things. We're going to tell them the course that semiconductor technology has taken in the intervening 50 years. We're going to tell them about billions of transistors on a piece of silicon integrated circuit. We're going to tell them about pizza-sized silicon wafers. We're going to tell them about how ubiquitous semiconductor electronics have become in our society. And we're going to tell them that the MOS transistor was the vehicle of all that. And I submit to you that I don't know which they would find more fantastic, the idea of everything that's happened, or that this MOS transistor was the vehicle through which all that happened. Because the MOS transistor met with a very icy response when it was first introduced by John Atala and Dawan Kong. And an engineer or a physicist or a chemist who was at that conference, who had a sense of history, would have recognized that what they were displaying was actually one of Bell Labs' missteps along the way to their initial invention of the transistor. That Bell Labs only really made progress in semiconductor technology with William Shockley's junction transistor, which sidestepped the problems of the semiconductor surface. And what Kong and Atala were doing was in some ways proposing to go backwards, to go and create a device that had all these problems of the semiconductor surface. And so it's not surprising at all that Bell Labs, in fact, stopped work on Kong and Atala's device shortly after the paper was presented at the conference. There was no formal publication after that. But within a few years after that, with the advent of John Herney's planar process and the integrated circuit of Robert Noyce and Jack Kilby, people began to see some promise in this MOS transistor. It was simpler to build than the bipolar transistor, and it could be scaled. Fairchild and RCA introduced the MOS transistor in 1963 in the context of integrated circuits. And when I say introduced the MOS transistor, I don't mean they actually proposed selling it. They just announced that they had this idea, that they were working on it, that they thought it might be good, but there were still many problems to be solved. And this set off an industry-wide research program to try to understand the behavior of the semiconductor surface and make stable MOS devices, devices whose characteristics would not change with time. And throughout the 1960s, groups of researchers at RCA, Fairchild, IBM, Bell Labs shared their work at IEEE and other conferences and argued about the sources of MOS instabilities. At the same time, people began looking for applications where the characteristics of the MOS transistor would make possible some product that had not been achievable with the existing bipolar technology. New companies were formed, such as General Microelectronics and American Microsystems, to try to exploit the possibilities of this new technology. One of the most ambitious projects of the time in the mid-1960s was the Victor 3900 calculator. It was the first all-MOS calculator designed by General Microelectronics. It had 20-some MOS chips, including a massive, for the time, 100-bit shift register. The calculator weighed 25 pounds, cost $1,800, and was impossible to manufacture. So these companies had a modicum of success, but they really didn't put MOS on the map at all. In the late 1960s, a new wave of companies were started to try and began new programs to try to implement MOS technology. These included such companies as Cogar, MOSTech, Four-Phase Systems, and one you may have heard of called Intel. And by the 1970s, a group of companies had developed reliable and sustainable MOS product lines. IBM had MOS semiconductor memories, which it used in its mainframes. Intel had developed semiconductor memories, the microprocessor, and EEPROMs. Other companies had other MOS products. Four-Phase Systems had an MOS computer. Texas Instruments and Motorola had MOS product lines, as did MOSTech. With these commercial products in place, through Moore's law, MOS scaling, and the use of ultra-low power CMOS, we can, without too much violence, extrapolate to where we are today. So in the late 1990s, I spent about 4 years researching the history of the MOS transistor, going through materials at Bell Labs, progress reports at Fairchild, progress reports at RCA, IBM, and other companies. And there are a number of interesting polarities in the history of the MOS transistor. One is the polarity between the existing technology, the bipolar technology, and the MOS technology. So we're by now used to new technology that is often hyped and overhyped, and often new technology doesn't pan out as it's been hyped. And so this was a question with the MOS technology. Would this ever amount to anything? Would there be ever any room for this technology in the face of the existing bipolar technology? And so that was one of the tensions the MOS transistor faced as people worked on developing it. And one of the advantages that the MOS technology had was it took advantage of the existing infrastructure that had built up around the bipolar technology. The next polarity is between R&D and production. The story of the MOS transistor is a great story of industrial research and development in the 1960s, and some of America's best-known R&D labs were involved and contributed mightily to this technology. There was Bell Labs, RCA's David Sarnoff Labs, Fairchild R&D, IBM's T.J. Watson Labs. Some of these labs no longer exist or are but a shell of their former selves. And while the work done at these labs was very important for the successful development of the MOS technology, these labs struggled mightily to create MOS products. And after all the problems that had been experienced at Fairchild, the founders of Intel made the conscious decision not to have a separate R&D lab as they continued to exploit MOS technology. A related polarity in the story of the MOS transistor is coastal. The MOS transistor was born in the East Coast, but ultimately found its abiding home on the West Coast, where startup companies were better able to exploit the possibilities of this new technology. We can't completely do justice to the story of the MOS transistor tonight. Many people have contributed. I'm honored to see a number of them here tonight. Since our speakers spent most of their careers at specific companies and institutions, these companies and institutions will be overrepresented in tonight's discussion. That's not to deny the work of others, but it just makes sense to focus on what our speakers can speak about best. So how did we get to this point? And that's what we're here to talk about tonight. And this is a story, again, to which many people have contributed, but we're fortunate to have three people with us who really need no introduction. There are three people that I interviewed about 10 years ago when I was working on my history who have really been major contributors to the MOS transistor, and it would be hard to think or imagine of three better people to have with us tonight. So let me welcome them to the stage, and I'll give them each a brief introduction.
Our seats are assigned.
Sure. So I'll start with Lou Terman in the middle. Lou is probably our senior MOS hand. He worked on MOS even before there was an MOS transistor. He did his PhD dissertation with John Mall at Stanford University on investigation of surface states at a silicon-silicon dioxide interface using MOS diodes. After completing his dissertation, he moved to IBM's research facility at Yorktown Heights, and after a few years of dabbling in other things, he got pulled back into MOS memories and spent the rest of his career there, and Lou was the president of the IEEE in 2008. On the far right is Les Videz. Les is also an old MOS hand. He started his semiconductor career at a small Massachusetts firm, Transitron, and he started his MOS work back in 1963, and wrote his first paper the next year. He later moved to Fairchild, first working in bipolar, before he headed an MOS group at Fairchild R&D working on silicon gate technology. Les was at Intel at the beginning and the head of MOS engineering there. Les subsequently was a senior VP of Intel and member of the board of directors. And so right next to me is David Hodges, who earned his PhD from UC Berkeley in 1966, and then went to work for Bell Labs, where he was involved in the prototype development of an 8K MOS SRAM for telephone systems applications. He forecast subsequent development of much larger MOS memories, and after pushing MOS memories at Bell Labs for a while, he left to join the EE department at Berkeley, where he concentrated more on analog circuitry, and he was the dean of engineering at UC Berkeley from 1990 to 1996. So again, thank you for being here. Thank you. So Lou, I want to start with you as, again, the senior MOS hand on our panel. Can you describe what it was like working on these CV plots at Stanford and when you first had the inkling that this MOS might amount to something?
It was pretty straightforward. I was walking down the hallway in one direction at the old SEL building, and John Mall was walking in the other direction. And John stopped. We'd worked on something before. And he said, I have this pretty neat idea for a thesis, which is in measuring the surface states of MOS devices, or of the oxide silicon interface. And I said, oh, that sounds interesting. And that was it. I happened to be walking at the right time at the right place, and so we worked on it. Mall was a great guy to work for. it was the ideal thesis topic because I was measuring surface states. I couldn't be wrong. Anything between the theory and the practical measurement was surface states. Nobody could reproduce surface states at the time, so it was the perfect thesis topic. It was a wonderful topic. And then when I left, went back to IBM, I went into a group that was doing logic design of a high-level Fortran-like language into hardware. And so I talked to a few people about it, but we needed a memory, and one thing led to another, and I got into MOS memory and said, hey, this looks like something that would be good because IBM was using core memory at the time. So it was just sort of a good thing on the thesis, then went to IBM and came back into where there was a real opportunity which I could see was going.
Les, could you tell us about how you got interested in MOS? You first started working on it at Transitron, is that right?
Well, I think I didn't really start working on it. I got interested in it. And so a colleague of mine, Dave Root, and myself started to try to understand it. And we even wrote a paper on it. But we never made any devices at that point. It was more of trying to just understand what the device could do. But it was very hard not to get really enamored with the notion that, gee, how many of these transistors could you pack on a small piece of silicon? And that really where my enthusiasm for the technology started.
So David, could you tell us, I mean, again, bipolar technology was doing fine. There weren't any problems with it. Could you describe your initial exposure to MOS technology?
So when I got to Bell Labs in 1966, I was assigned to work on a prototype development of an 8,000-bit memory system for a PBX, where at the time the cost of the ferrite core that was being used, the complete system, was $4,000 for 8,000 bits. So our group thought we could do better, and we had just a 24-bit PMOS chip, bipolar, discrete, beam-leaded circuits around the periphery, and we actually made a working model with the help of a brilliant technician, and that was sufficient to convince the management to proceed with a development at Allentown of a small memory. But I have to say, at the time, there was no confidence in the reliability and quality control for MOS for use in large systems, and that burden lay over our MOS work the whole time I was there.
So Les, you had mentioned you thought of something big. How big did you think of? What was your sort of wildest imagination when you were thinking about MOS in those days?
Back in those days, if you thought about thousands, then it was way out of the reason. I mean, you were really talking about it. The problem with MOS at that time was that it was more of just a vague notion of what you could do with it. Rather than anything specific that gee, I want to do this. And it was more of the concept of packaging a lot of transistors on a small piece of silicon. And it's really later when I came to Fairchild, that's when I recognized that there are some minor issues, that the device is really hard to make. It's not very stable. By the way, perhaps we ought to recognize that two of the people who really put the scientific underpinning to this technology are here with us today. My good friends Andy Grove and Ed Snow are here, and really, they were the one to me who explained why is it so hard to make. What are the problems? And everything came after that.
And just going back to you, David, for a second, Bell Labs was, I guess, famous or infamous for, as you said, sort of its lack of faith in MOS. Why was that, do you think? So Les had mentioned there were some of these problems, but why do you think Bell Labs was so resistant to this technology?
You know, they always used to talk about the 40-year life, and their equipment would last forever, and they would build the undersea cables that had to last forever. And the data that was available at that time on MOS was just so far short of what they wanted to build into the telephone network that they said, we'll have to stick with these proven, reliable approaches. And some of the early work on the silicon gate was done by Jack Serace, whom I knew there at the labs. And while it was clearly a superior approach to building the transistor, when they transferred our prototype memory to Allentown, it was still stayed metal gate. They just couldn't convince themselves to take the risks of something unproven.
And it was in some ways, you think, in Bell Labs DNA, I mean, sometimes there have been criticisms of individual managers or critiques of individual managers, but maybe you might say it was in Bell Labs DNA to resist a technology like this?
There were elements of both of those things. Mike Reardon has written a wonderful article in Spectrum from December 2006, I think, how Bell missed the integrated circuit. They just didn't. There was a memo circulating at the time that said the maximum feasible level of integration would be 2 transistors or 6 diodes per chip.
So I've read a thing where Gordon Moore once said that MOS was a religion as well as a technology. And so would you, I want to ask you if you were sort of inductees into this religion or if you were agnostic. Maybe we can, you can profess your faith in the 1960s in this technology, and maybe we'll start with Les and go across.
I was a practitioner. I really believed that religion, if you will. The problem was that it was more of a belief system at that point. If you looked at the world about what the business was, the bipolar business was, the bipolar people were right, because MOS never replaced that business. You had to go and develop a different business and at a different level in order to create the business what we have today. So we all were looking at what it could be, not what it was. And many people just look at the business of what it was and says, hey, this technology will never replace what we have.
Lou?
Okay, Les is wrong. Bipolar he says that bipolar was never going to be replaced by CMOS or MOS. But the mainframe computers, which is where bipolar is really shown in those days, have been replaced by CMOS because of the power requirements. So bipolar lost a lot of it. It still does have the edge at the very high performance. All technologies have a gestation period, and it generally runs at least 10 years. It took 10 years for the transistor, between the transistor's invention of bipolar to where it was being used in products. And it took roughly 10 years of MOS, not quite that much. MOS, you can look at it and you can say it's the natural for integrated circuits because it has an interconnection level. It had 2 levels of interconnection, the metal and the diffusion. Diffusion wasn't a good interconnection, but it was a natural for integrated circuits. And you could see there were things that didn't require the power of bipolar, or the performance power of bipolars, watches, calculators, that sort of things. There were products for consumers that didn't require the big performance ability of the bipolar, where the cost would drive it. And MOS was going to be a cheaper cost if you had faith. You had to have that faith, and you had to be willing to wait out that 5 to 10 years while it came into being.
But so, Lou, it must have been harder to have that faith at IBM where the mainframe was so dominant and bipolar was then so dominant.
But the door that opened was memory, because they were making core memories, and they said they had to go faster, you had to shrink the core. They had these wonderful wiring machines that put the 3 wires through the XY select and the sensing wire through the cores automatically. But you drove these things with amperes and you got millivolts out. It was a terrible system, but it was non-volatile, and it's about the best way to make a memory. But they realized that they just were not going to be able to make the memory at the speeds they were going to need in a generation or two. And so we were doing the innate perversity of research was we were working on in-channel technology. I had done some work with a magnetic film memory and looked at this and said, this is a terrible way of doing things. Let's try to put a circuit at each memory spot. And that, plus this work that was being done in the research division, plus the need of the corporation to have a memory system that would be able to have accesses of 250 nanoseconds or better, led us to where we wanted to go, namely that came in, people said, yes, you in fact can make these devices. They are stable. There was a lot of effort that went into making them stable and having the reliability that was necessary. But that was the door. Without that, we would have been stuck with bipolar memories, which would have been terrible. They would have been 60 to 128 bits per chip, and the densities would have been really bad, and it would have been it impacted the system performance.
So David, were you a believer?
I was kind of agnostic at the first. My boss said, go ahead, see if you can speculate on the future of semiconductor memory, and I did write a paper about 1966, and it covered bipolar and MOS, but the density advantages were already clear, and what I didn't fully appreciate at that time was how much better the MOS would fare with the scaling that came on so rapidly. And so rapidly, I became a convert to MOS as the best technology for memory.
So my sense is that often you need some people who are believers and then some people who are agnostics. My sense, Les, and maybe you could correct me, is that Gordon Moore was, through a lot of his time, sort of an agnostic or not necessarily a believer, someone who wanted to look at it more rationally and maybe was not as enthusiastic as others. Would that be your sense of his, the way he looked at it in the Fairchild days?
Gordon is a very rational guy, and he looks at what works. But I really cannot speak for him. Mm-hmm. Many of us just go with the dream.
Yeah. Mm-hmm. So I want to talk about and we've kind of mentioned it, but what were some of the impediments to this technology? What was some of the problems that we had these problems of stability? How were they solved? A lot of people didn't believe that it would be possible to make stable MOS devices. How did that issue get resolved?
Me?
Sure.
Well, to me, as I said, I learned the good and the bad and the ugly at Fairchild R&D. And I clearly remember started to work on device using molybdenum gate for a couple of purposes. One was to create a self-aligned structure which had less parasitics, hopefully better performance, but more importantly, that you could do high temperature processing after the gate was, the active device was defined. And it was a mess. I couldn't make it work. But that's when I heard Ed Snow reporting on Bell technology development on silicon gate. And it was kind of an aha. This is the way to make a stable device, because you can do high temperature processing after the active area was defined. And he also ended his report that, well, by the way, Bell discontinued the process. And so my claim to fame is that I took it out of Bell Labs garbage bin.
What kind of, so David or Lou, what kind of sort of conceptual problems were there with MOS? Did it require new ways of thinking about transistors that maybe were not natural for people at the time?
I think it required thinking at a higher level. It really didn't pay off to think about a single gate as a product or a register as a product. You had to think on a larger scale, and mostly people in device technology at that time weren't trained to think at those higher levels. That was the province of people who designed boards and plug circuits into them. So we had to sort of cultivate that larger scale thinking, but pretty quickly it became clear that the memory was a very natural place to start. And I think even if Intel had not been established when it was, that somebody else would have come along, maybe not so quickly or so successfully, but memory would have become a very major focus for this, making good use of a capability for a higher level of integration.
Yeah, I think one of the important things with the memory was that you used hundreds of sense amplifiers, hundreds of selection and drivers and so forth, but you only had to design it once. So you went in and you designed the circuit to really be correct and perfect within that area, within that application, and so you understood things. You understood how the devices worked. You had modeling programs that actually were pretty good, even though they were relatively small numbers. But you weren't designing lots and lots of gates of different types and different loads and everything. You did a lot of custom design, but you got to know things pretty well, and it was relatively simple to design the relatively small number of circuits that you needed, rather than a whole bunch of gates for a processor, for instance.
And Lou, I guess this was, I think, before you were involved, but IBM had a big MOS Logic array program,
yeah.
Right? And then what happened with that? Could you describe that MOS Logic?
Yeah. Research had a 55 circuit chip that did logic and so forth. And they had a light table that exposed the masks so they didn't have to cut rubylith, which a lot of people were pretty happy about that. But the focus went on to memory. From the 6-device cell, which we used in the mainframe memory, we then went into using the 1 transistor cell of didnt. But that was aimed at the smallest possible cell, and so we went into what's called the CMOS process, which was a totally useless process. It only made a small cell. It was terrible for logic because it wasn't self-aligned. And when we did finally come out with the first 64 kilobit chip, it was reported in the press as being the largest, slowest, and highest power 64 kilobit chip that man had ever made. And it turned out to be that. And it was a lousy process for logic. So it took a while for logic to get in.
And that's when IBM bought a big chunk of Intel.
Yes. And unfortunately, we sold it.
So did any of you in this, I mean, there was a time in the mid-'60s where MOS, was not going anywhere. Did any of you ever lose faith or just imagine this, that there were all these problems of MOS stability that even when, after the work of Andy Grove and Bruce Steele and Ed Snow, there were still, I see, problems making stable MOS devices. Did any of you ever just consider throwing in the towel and saying this will not work?
There was no alternative. MOS memory was it. Magnetic films had never really made it. Cores, we just simply couldn't meet the performance requirement. That was it. You had to make the device. We had one wafer at IBM Research that was stable, and that kept them going for a long time until we figured out how to keep the impurities out and how, if they got in, how to keep them from moving and get a stable transistor.
I recall it was number 3707, I think is what Dale Critchlow told me. David, were you going to say something?
No.
But there were people with small companies who were coming out with products.
Mm-hmm.
There were calculators and that sort of thing in the watch business. There were products out there that didn't need high levels of integration, mm-hmm. And where cost was really paramount. Mm-hmm. And that was something that kept things going,
yeah.
and kept it alive at the non-memory level.
Well, again, yeah, that's the point, that MOS devices were being designed, but it was very hard to find things that were high enough volume that you could amortize the investment needed to create the product. Plus, I don't know what happened in IBM, because at that point IBM was not in the merchant market in the semiconductor area. But in a merchant market area, I have a feeling that we were running ahead of the technology capability, because we were designing these products, and the technology was really not strong enough. And I think that some of the things that you mentioned about the problems companies ran into is because they couldn't manufacture reliable product consistently. And that's where I really feel that that consistency came into the merchant market with the introduction of Silicon Gate.
Yeah. Sometimes the argument has been made about Fairchild that just like with Xerox PARC, there's this, story fumbling the future. Sometimes their argument is made at Fairchild that, well, they did all this great MOS work, but they never made any products. And I guess I'm not sure if that's a fair argument against Fairchild or not, that no one was really making a lot of MOS products at that time. There was a lot of uncertainty in the industry. Maybe, do you have any sense about?
There are a lot of small companies spun out of the Fairchild work. So I think that what you saw there is really the issues with central R&Ds, that they spun out more technology outside of the company than inside the company.
Did people ever leave Bell Labs or IBM the same way that they left Fairchild?
Yeah, but not to the same level. You know, I think the flux through there might be 10% a year, and in the Valley it was 15 or 20% or 30%. But a lot of people left and tried starting. There was the Kogar thing, which was a big defection from IBM. Went flop pretty quick.
Yeah, Kogar kind of spun out of control, so to speak. No, but IBM kept its people pretty much. It was supporting the work. It was clear markets. They were moving forward. But it seems to me the real thing was the microprocessor. That was the real point where you got something that you can make in millions, sell to people, and could have all sorts of applications.
Well, before that, we sold huge numbers of memories. And the dynamic RAM concept really was unique to MOS to start with. And I mean, our first dynamic RAM was the most horrible device to use man and beast ever invented, but it got the ball rolling. And I think that other refinements after that created a $10 billion business today. But in fact, when we after the microprocessor story unfolded, and back in the middle of 80s, we got out of the DRAM business. One of the internal debates about why we shouldn't get out of the DRAM business is that we needed the volume driver for new generations of technologies. So DRAM, or memory technology generally, was a very high volume technology and was the first vehicles in the early age to develop new generations of technology. So it was a very interesting, both from that point of view and also really that drive the initial market.
So do you think Intel, if it had come up with the microprocessor first without the memory to support the company, could it have survived and been successful as just a microprocessor company without the DRAM?
I have no idea. I mean, the whole thing was a very serendipitous development. And that's probably the most interesting part about it, is that there was no forward planning that we're going to make a microprocessor. So there was no forward planning that we're going to make a non-volatile memory. It was more of a recognition of what we had and how we went about creating it, which we may want to talk about, because I think it's a...
But the cheap, so if the microprocessor had come first, it would have needed lots of cheap memory. So you would have been forced into that. When I said the microprocessor, I meant the logic, from the logic standpoint. The microprocessor would have made logic. The DRAM was the driver for 2 decades, and then it became too routine and it stopped being the driver. And of course the technology separated too. DRAM went off in its direction, much more complex than was necessary for the microprocessor.
So David, just as, again, as a counterfactual, do you think there were a lot of these things were developed at Intel, but if we were to imagine, say, Intel had been wiped out, if there had been some fire at 365 Middlefield Road, would the industry have taken the same course it took, do you think, or would it have gone in some different direction? Was it sort of tending in that direction on its own?
Keep in mind, at that time, we didn't know about the scale of IBM's commitment to memory, but that would have come out without very much delay. And everybody would have seen the natural fit with memory. And so I think that it might not have happened so quickly and become so readily available because Intel did a superb job of execution. But absolutely, it would have, in my book, it would have followed the same path, perhaps with some delay.
Well, so you are here, Les, and you can, what do you think?
Well, you know, I mean, I think the industry would have moved forward as always did and always will. I can't, but I want to go back to the microprocessor a little bit. I think most everybody knows the story of the microprocessor, how it came about. And by the way, Federico is in the room here. Federico Fujim was one of the key guys on that. Pat Hoff and Federico Fujim has done a wonderful job of creating some products that really we all know and identify with. But there's another side of it which doesn't get as much notice. At that time, when we had that device, people who created computer system kind of poo-pooed it. It was very, very mediocre performance compared to what they needed. People who could use it didn't know anything about how to program devices. And I think the introduction of those set of devices with the development tools, the in-circuit emulator, and training programs of how to use it contributed just as much to make that what it is today than the clearly wonderful technical development of creating a microprocessor. And of course, roughly around the same time, EEPROM happened, which was a very essential element of the whole story. So there is more to the microprocessor than the chip story. It's really a business development story as well. Yeah.
David, when was it clear to you that the microprocessor was going to be a big thing in the industry?
Really very quickly, and we immediately got some 4004 chipsets and set them up in the teaching labs, made little boards, and had the students all learn. Now we would call this embedded control or something. They'd flash lights or actuate something. The students loved it, you know, and it was perfectly clear. By then we all knew the story that Les told me a few days ago drove them to it. He didn't have enough designers to design all the chips that would have been needed for that Visicom, and the best solution was to have a programmable design. And you know, the minute that became feasible, for $100 or whatever, it became pretty clear to a lot of us that that was going to be a very important step forward and would have a huge impact.
But many of the competitors of the day absolutely poo-pooed it, both from the chip side and from the system side.
It wasn't their idea.
And I guess, Lou, there was sort of a sense that I've spoken to people like Dale Critchlow who said, you know, we knew something like this was possible, but it wasn't really something that IBM could make into a product, so it wasn't really possible in the IBM environment to do something like an microprocessor as a product. Would you agree with that?
Yeah, IBM didn't have its view on small local processing capability. It was big processors, that's what they built, that's what they made their money on. And that's what almost killed them off in the downturn in the early 90s. They just missed that whole change in the industry. And so we eventually got to the point where we were starting to design local processing things and spread processor and workstations and that sort of thing. But it took a long time, and we had to have the technology to do it, and we were very slow into getting into that technology. Les brought up an extremely important point. The whole EDA, the CAD tool development, which enables us to design things, large chips, get them right the first time. You make them, they go in, you test them, they're right. There's no errors in them. That's incredible. Considering what people were doing 40 years ago, that's another miracle that we've done. The fact that we can yield these chips is one thing, but a second miracle is we can even design them.
Yeah. Do you think, Lou, is there any way that IBM could have, I guess So having worked at IBM, I have the sense that IBM left some money on the table with MOS, that they did a lot of good work but didn't benefit from it as much. Is there any way that we could imagine a scenario where we don't have to say dogs are flying or something crazy, but we could imagine that IBM taking better advantage of MOS than they did if they had made some discrete managerial decisions, or is it just that the forces were against them?
They would have had to start a division with that focus to do it. They would have had to change the technology within this critical 1970s era of the CMOS technology, got rid of that, gone to Silicon Gate, which we were very late in getting into, and then go to CMOS, which we're also late getting into. And just give somebody the responsibility to find the market and design the things. We had the technology foundation. We had to design the technology for that market and then start doing things. We were late doing that, but eventually IBM got into doing it and actually does it pretty well nowadays.
I really, again, this was not just the issue of technology. It was also the issue of business strategy of the company. And if you look at what MOS microprocessor-based machines have done, they have totally undone the business of what computer companies created. Now, it's very hard for a computer company to say, gee, now we're going to undo our business.
Yeah.
It's very hard for any company to do, to say, gee, we're going to undo the business we have and we're going to go into a new kind of business. And so I think that system companies were always at a disadvantage in doing things like that. Disruptors were us, because our industry was really the one who benefited the most.
Yeah. So, David, you moved to analog devices at UC Berkeley. Could you talk about how analog, how CMOS entered into analog and analog MOS became an important technology?
Sure. So even while I was at Bell, I had this vision that the other functions beside the memory and the processor in a telephone exchange could be made with MOS, but they had to be a lot of analog functions. And so I started thinking about it there, but I got no traction with that because there was established group, established technology doing it the old way, and they weren't really interested in new technology. So at Berkeley, though, I had the chance, and I had some NSF support, and we had very good cooperation here in the Valley from particularly from TRW Vidar and Jack McDonald in sort of really understanding what you need to do for when you've got the wire coming in from the street with the analog on it and you want to get into a digital switch. And Bell always did this with a time-shared thing, 12 channels per card. Nortel said, hey, we want to do this with fully integrated circuits. So we had worked on A to D conversion and filters and built prototype chips and demonstrated we could meet the telephone spec, which is a tight spec. And Bell wasn't interested, but Nortel picked it up, and Nortel went in the telephone exchange business from $1 billion a year to an $8 billion a year company in 3 years by taking the market for with the DMS 100, which is what we all talk over in California. When you pick up your phone, you're going through a DMS 100 switch made by Nortel, now a bankrupt company, but it was 5 or 10 years ahead of Bell in terms of applying fully integrated mixed signal, precision analog, high density digital, the same chip. And I had dye photos here that we weren't able to project tonight, dye photos of their first 2 generations of the line card chip, which had about half the area was analog and about half was digital. It was all a standard CMOS process. And that's when MOS became visible as really the technology could do almost anything except the megawatts and the microvolts.
Another kind of key point in MOS was this switch to CMOS, that some people had, from the very beginning, Frank Wanless had the original CMOS patent filed in 1963, I guess. RCA was very big on pushing it. How was it that CMOS became, and then it was essential for use in digital watches and things like that, how was it that CMOS became a mainstream technology used for microprocessors, memories, and things like that?
It was very simple. Oh, go ahead. Power. Yeah.
That was the second line of defense in power. First line was MOS, any MOS. Second line was CMOS. And since then, we have third, fourth, fifth, and sixth line, and we still live with that limitation.
Yeah, it was somewhere around 1980, Dick Pashley of Intel gave a paper on, I think it was a 4 kilobit NMOS static RAM, and it was 50 nanosecond access. Everybody was wiped out by that. The next year, Masahara of Hitachi came in and gave a paper on a 50-year sub 50 nanosecond CMOS access static RAM. And up to that point, everybody said CMOS is slow because you got this really slow P-channel device doing a pull-up. It's terrible. And you got 2 gates you're driving and so on. And he showed that it, in fact, was fast. And by the way, it was done at about, I don't know, 1/4 the power. And the next year, you could go down and you look at the NMOS processors and the CMOS processors, roughly the same performance. And the CMOS processors were all 1/3 to 1/5 the power. And everybody was talking about power. That was it. The writing was on the wall.
But I guess there were some, again, you could be in the industry and be in some of these technologies too quickly. Like I think RCA made the, in retrospect, mistake of pushing some of these technologies too quickly before they really hit their sweet spot, it seems. So in just looking at things general, just what the MOS experience tells us, in your experience with the MOS technology, have you seen sort of that story play out in other technologies as you've seen other technologies develop either in the computer industry, or do you think has the MOS story been something that's largely unique and not replicated in other technologies, that sort of the main elements of this story?
Go ahead. No, it's an interesting question because if you look around now, the original bipolar companies, they don't exist except for IBM, which doesn't do bipolar, except in the very, very high performance heterojunction devices. So the clear argument is that you can introduce a new technology and it's going to be new companies that take that and really move it forward if it's really a successful technology. And I think that happened too when semiconductors came in and the vacuum tubes went out, basically. On the other hand, I can give you an example of the magnetic storage, where there's been just as much improvement in magnetic storage bit density as there's been in the MOS world. And I think it's the same companies that have been doing that. IBM got out of the business, but that's continued on pretty well. There's been some change of companies. So I think, though, the MOS, because it wasn't just one thing, it was this, what it brought out is this tremendous broadening of the applications, the things you could do with the processing capability. No one company has the understanding of all the things that can be done. And so starting all these companies and to do things really worked out, I think, extremely well. And that's why we see the MOS companies really have spread out and dominated the new ones rather than the old ones.
David?
I think what we haven't noticed enough is that some of the biggest and fastest growing companies have really profited by bringing real high-level systems thinking down to the chip. And I'm thinking about Qualcomm and Broadcom and Marvell, all of the multi-billion-dollar companies. By the way, they don't manufacture chips at all, but they bring system thinking into the reality of a single chip silicon realization. And this is something that took years to develop. That thinking was Broadcom, the founders of Broadcom came out of TRW, out of military, very high performance military systems, and putting that function onto a chip. That took some years to learn how to do it.
So Les, I guess Intel had that systems thinking for some time as
well. I think Intel, if you want to use MOS, I think you needed to have the knowledge assets about 1 or 2 levels above the food chain where you were participating, because you really need to understand how you're going to fit that into a system environment. But to me, what's interesting about the MOS story, it's really two things. We were talking in one of our early discussion that the first patent on MOS was issued in 1928, you said, to somebody, Lillian Field. Lillian thought, yeah. 1928. The technology wasn't really viable until the 60s. And then now you look at that technology of how many different permutation and combination you have. You have the basic logic. You have the non-volatile memory. You have the dynamic RAM. You have all the imaging devices. You have now some MEMS. And the story is not done yet. The flexibility with which you are able to use that foundation technology is just awesome.
And so what has it been that's driven this industry? Has it been the technology? Has it been the business models? What would you say has been?
It's a yin-yang.
Back and forth.
It's products provide you the revenue to invest more into your technology, which gives you more products that, et cetera, et cetera. And the more successful, the more broadly it's used, the more you move the technology forward.
Yeah, Jim Meindl at the last ISSCC at a keynote speech pointed out that the productivity of MOS has increased by 10 to the 9th in the last 50 years, and that the speed has improved by 10 to the 6th. If any technology had that improvement and you can't find something to do with it that's unique, forget it. Get into a different business.
So we've sort of touched on this a little bit, but what do you think this story tells us about startups versus large established corporations? It seems like that startups have had some particular advantages in exploiting this technology, and what do you think that the story of MOS tells us about sort of that relationship?
The innovator's dilemma is right. The Clayton Christensen book. It's so hard for a big company to look at their billion-dollar business and say, how is this upstart? My customers want a little bit better and a little bit cheaper what I'm already doing. They don't want something brand new. So it's almost inevitable that the startups will be the only ones that are willing to take the risk.
I think there's an interesting point. MOS really got its momentum going in the beginning because of large research laboratories at IBM, RCA, Bell Laboratories, and so forth. And that's gone. So the only place you're going to get that innovation where you can do something, somebody will give you some money, you got a chance to do something with it, maybe you'll get rich, is through the startups.
Yeah. So David, what role have universities played in this process? So in some ways, one might think with the R&D labs gone that we might ask the universities to step up to that task today.
Well, I think the universities can do some of this, but it's no way is it a full replacement. And we can work most successfully in partnership with people in companies who have a little bit of latitude in terms of some time away from their principal project to give us input and feedback. And we have had a lot of projects. Our analog MOS all worked that way. We had a wonderful group of people. We're going to have a session here in February about SPICE. That was all done at the university. And tremendous two-way connections with people in industry who were interested in the work but didn't conduct all of that work themselves. And I've spoken abroad frequently on this because I think that's our secret weapon in the United States is that we do this better than any other country in the world. We have meaningful collaborations between university and industry.
Well, it's not an either-or story, although in most cases, startups, I think, have done better in creating business in areas where the business model really had to change in order to take advantage of the technology. But, there are cases where established companies, I look back and say, gee, at least for a while, TI shipped a lot of MOS. Maybe today, TI ships a lot of MOS. And TI didn't start out as an MOS company. So it happens. It happens. But when business models have to change, established companies are at a gross disadvantage.
So I have one last question for you all, and I guess it's in some ways the inevitable one for something like this. How much longer will the MOS transistor be with us? And I guess I'll warn you so that it's being recorded, so your answer, you cannot deny your answer at a later date. We'll start with you, David.
It'll last at least 10 years beyond the appearance of something the three of us believe could be its successor.
So I'm assuming that hasn't happened yet.
That hasn't happened yet.
Yeah, the MOS device is going to keep on going and being a major player for the foreseeable future. Even if something else comes along, we've driven the price down, the performance is up, and it's up to you guys in this room to figure out what the next big application is, because you can make a lot of money just taking today's technology and applying it. And people are out there working on it to improve it, improve the technology.
Lou, you have a chance to be a contrarian here and give a different opinion.
No, I can't. I think it's going to go on, but I think it also, we are going to be build on it more technologies. It may be the scaffolding to many other technologies to come. And as long as we keep creating the kind of products we have been, it's going to live longer than I am, and I intend to live a long time.
What's the biggest growing field? That's the services business. It's converted IBM, and a lot of people are doing that. And that's using all this computing power and capability at a systems level. That's where it's going to be, keep on going and making things better around the world.
So as we think about this remarkable technology, and as I looked at it myself, one of the things that just impressed me was the ecosystem through which this was created, the many innovations created by many different people, some people who weren't there when the technology was there to make a lot of money. And I think there's a wide variety of people, a wide variety of organizations that contributed mightily to this. We talked about the large companies like RCA, Bell Labs, IBM, but then also the startup companies, and it's really a testimony to the vitality of the American innovation system that we have the MOS transistor today. So I want to thank you all for your comments, and we're going to turn to some questions now. And I guess I'll let you, we have first, at high levels of integration, how much innovation is held back by the first chip cost? So would anyone like to?
I don't understand the question.
At high levels of integration, so I guess very high densities, how much is innovation held back by the cost of making the first silicon wafer?
So there's a wonderful solution that works for many people, and that is the FPGA, which is a very quick turnaround way to test your ideas and see if they work. And I believe that companies like Cisco, for instance, prototype a lot of new products this way, and if they turn out to be a big winner in the market, you could take the tape for the FPGA over to there's a specialty house or more than one, that will convert it to a much smaller, lower power chip. If you're going to make 1 million of them, that would pay off. So we have a path to the high complexity that didn't exist realistically until FPGAs got up to a really useful size.
So here, this may be for you, Lou, or maybe anyone. How early did it become clear that MOS was going to be as scalable as it turned out to be?
From a memory standpoint, pretty early. Once we realized that we had a market, and we saw these guys from Intel coming in and suddenly making these things that look good. I think Dave, wrote an article that MOS memories win, about 1972 or so, something along that line. And I remember a panel session around 1970 or 71 where a guy from a thin film company said, no, you guys will never be able to get the yield. But within 2 years, he wasn't attending our conferences anymore.
He was out of work.
He was out of work, yeah. But again, with the logic, you were looking for small things until the microprocessor came in. Boy, that just changed the whole game. Not the first one, that was a little small, but as you went up very quickly, boy, you could see that was just going to be something that people could do. And it was more your imagination as to where those applications were than the limiting of the technology.
That became clear only 2 or 3 years after Moore's Law was promulgated, and we all finally believed it.
So when you say Moore's Law was promulgated, do you mean the 75 incarnation of that at the IEDM or the 65?
The 65.
So you believed it a few years after that?
2 or 3 years after that, I say, that's amazing. And by the way, you started thinking about, well, what's the impediment? Why can't it keep on like that? And you had a hard time thinking of what the impediment was going to be.
So this is for you, Les. What does Intel see as the most likely disruptive semiconductor technology today, assuming ability to forecast the future? What can topple CMOS? So,
First of all, I have no idea. I retired from Intel 7 years ago, so I have no idea what Intel thinks.
That question was also for Andy, by the way. He can answer it.
What?
he said it was for Andy too, but.
He retired too.
Yeah.
But I think that it would be very dangerous not to be paranoid about looking at all the various technologies that are around, because, you know, convinced that the MOS story will repeat itself.
So
That's what technology is all about.
So only the paranoid survive still holds.
That's right. That's right. That's right.
I think if anybody here knew the answer, he or she would be a wealthy person in 10 years.
What constrained technology generations to 18 to 24 months? Why couldn't any companies leap forward by, say, 2 generations instead of only by 1 by leapfrogging?
Well, I think, you know, there's no physical law which says, you know, Moore's law is law of physics. What it really is almost like an unwritten agreement between the various participants of the ecosystem, be that photolithography companies, be that other equipment companies, and they are very much sort of together in moving the technology forward. It's not one, it's many things that move the technology forward. And everybody kind of salutes and says, okay, we have to be on this line. And so they develop their technology as fast as they can to be on that line.
But if you look at the progress, when the semiconductor map was put in the mid-90s, and everybody said, well, it's going to project down like it has before. Here's what it was before, and it's going to project down. And suddenly everybody said, well, if that's where the rest of the industry is, I can be ahead. And all of a sudden, that line moved much faster because there was a driving force behind it. I think people suddenly realized, hey, we can, in fact, move faster. And we, in fact, did. There was it wasn't a step function, but there was a definitely increase in the slope of that line.
So, David, I think you might be the best equipped to answer it, but it may be, why did Bell Labs not accept the idea that planar 2 or sodium-free oxides were necessary for stable MOS structures? That may be a little too deep in the mud, but I don't know if you have...
Well, they're always striving for the fundamental answer to the problem, right? It was just where was the focus of resources being devoted. In that moment of time, the late 60s at Bell, the focus was on getting that number 5 ESS out. They didn't know about Nortel at that time. They had their in-house technologies all committed, and really all the focus was on the embedded there in-house technologies, you know, tantalum thin film analog, and ferrite core, ferrite sheet, or plated wire memory, and collector diffusion isolation bipolar. And so, because the problem you just mentioned about sodium and so on didn't really reflect on the highest priority development schedules, it just didn't get the attention. And a wonderful guy like Jacques Serres got discouraged and went to RCA after inventing the practical silicon gate process.
So, Les, here's a question for you. How did Intel's approach to research differ from IBM, Bell Labs, et cetera? How could Intel succeed without central R&D labs?
Well, the most important element in our activity was, in my mind, the moving of actually people with projects back and forth across the line. not to create the sort of the hard walls, throwing technology over the transom and re-engineering the technology on the other side, but really trying to smooth out these transitions. And I think that for a long time, that worked very well. Now, I think if you look at today Intel, there are some pockets of research activities which are really removed from that. That transition, to me, is the key. And if you have a rigid interface, technology dies at that interface.
In some ways, did Moore's law require a company to have a very low time constant? Would you say that you have to, that you move things very quickly and you have to be, would that have been part of your?
I think you can move much quicker in this kind of, I mean, to me, the best story is the EEPROM. EEPROM was between the discovery of that device and the device of the explaining the phenomena, proposing a device, doing some conceptual market testing, developing a product and introducing a product was less than 2 years. I don't think you can do anything like that in the central research, development, manufacturing, kind of very traditional organization.
Here's, this may be our last question. As for MOS stability, which was the larger problem? Process stability, batch to batch, or device stability over its lifetime?
Yes.
Next question.
Yeah. Well, okay, so this will be our last question. Where do you see the future of MOS transistor going? Can we go below 20 nanometers and still achieve the same functions as now?
We're all retired.
Yeah, so that may have been too much to ask for three people.
We always 3 generations away from the wall.
Yeah. So yeah, don't predict that you can't do it. That could be a big mistake. Because if you're wrong, then you're out of business.
Well, I want to thank you all for sharing your insights and sharing this history with us.
Thank you.
Ross, thank you so much for your presentation and for leading a great panel. And let me also say thank you to Les and to Lou and to David. You've just been outstanding. Thanks very much. And you can see by the turnout tonight, it's a subject that has a tremendous amount of interest, especially in this part of the world. So thank you. We have a small gift for each of you for participating tonight. It's a book published by the museum. It's called Core Memory. We have a brilliant young photographer, ironically enough, Core Memory, named Mark Richards, who treats the computers and the other artifacts in this museum as works of art. And so we've got a book and some great text for you as a thank you gift. So please join me in thanking everyone up here on the stage again, and we'll see you on Thursday night.